So we've talked about a lot of different information here. We've talked about our goal, our objective, which is to minimize the cost of meeting electricity demand. We've talked about the constraints on this problem. We need to first meet electricity demand in every hour of every day, while also adhering to existing transmission line limits, the ability of to send electricity or not from one area to another, as well as plant-specific limits like maximum generation capacity, operating flexibility like ramp rates, minimum up and down times and start times, etc. We want to incorporate that information along with all of the economic information we have for all the different power plants that are in our portfolio. And we want to incorporate all of that into an optimization to find the least cost generation schedule at each location in the network. And so there are lots of different ways for doing this. Ultimately, this is a pretty complex problem to solve with a lot of constraints, and is typically done through computer algorithms. And so the outcome of this type of the unit commitment economic dispatch problem is a schedule. And it gives us a schedule of how to use all the different power plants at every point within our system in a way that minimizes the cost of meeting electricity demand everywhere. So it would tell us about electricity production within each zone. So we could think about all of these different nodes within the network as different zones. And so zone one might have a certain pattern of electricity production from nuclear, coal, natural gas, and hydropower, et cetera. Zone two, another node in the network, might have a slightly different pattern. And zone three might have an even more different pattern. And we would also get information about how much electricity is going to be sent between these different zones at each hour of every day. So how does this conversation of the unit commitment and economic dispatch process relate to our microeconomic theory of wholesale electricity markets? So remember, when we talk about wholesale electricity markets, we started out by thinking about supply and demand, as well as how they interact to create different prices for electricity. So remember the wholesale price of electricity we're going to estimate here as the point on the y-axis that's associated with the intersection between the system supply curve and demand. And so we, in the past, were sort of assuming that the system supply curve stays constant and stable, and it's demand that's going up and down, which we're representing here as this vertical, perfectly inelastic demand curve moving left and right. So we should re-examine this assumption that the system supply curve is static, in other words, that it stays the same. Based on today's discussion, do you think that it's a good assumption that the system supply curve is always going to be the same? In reality, it's not. The system supply curve changes too, and that's based on resource availability. For example, some hours hydropower, wind, and solar might not be available, as well as engineering constraints. If there's 1 hour when an inflexible coal plant is not online, it's unlikely that we can assume that it's going to be online in the very, very next hour as well. We might have to start it and wait 24 hours for it to be able to produce electricity. However, apart from the fact that we now know that the system supply curve does change every hour, potentially, and every day, the unit commitment economic dispatch process, the process of finding the cheapest way to meet electricity demand, is not inconsistent with our microeconomic theory of wholesale electricity markets. So before we were talking about the prices being set by the intersection of supply and demand, and that's true. Another way to think about it is that competitive wholesale electricity prices are set equal to the dollar per megawatt hour cost of electricity at the most expensive plant that's used or scheduled to meet electricity demand. So let's take a look at what that would look like. Let's say that this is our generation portfolio, and we have different types of power plants, hydro, nuclear, coal, natural gas, etc. And each one of those power plants is associated with a different installed capacity in megawatts, a different variable cost in dollars per megawatt hour. And we can organize these plants in merit order, which remember means in order of increasing costs. And as we do that, we can then calculate the cumulative capacity that the system can provide. So the row 1 cumulative capacity would just be equal to the capacity of the hydropower plant. Row 2 cumulative capacity would be equal to the capacity, the joined or the summed capacity of the two hydropower plants. And row 3 cumulative capacity would be equal to the total capacity of row 1, 2, and 3, and so forth and so on, all the way through down to the last row. And so we can plot cumulative capacity alongside the variable cost rate in dollars per megawatt hour, all of those ordered pairs, and they give us this uniquely shaped system supply curve. And that system supply curve, again, can be used to estimate what the price of electricity is in wholesale markets. So the market clearing price, which we're going to refer to as the intersection of the system supply and demand curves, is equal to the dollar per megawatt hour cost of the most expensive generator needed to satisfy demand. So while the first might be something that we get out of microeconomic theory, the second might be something that we get out of the results from a unit commitment or economic dispatch problem. So let's take a look at a simple example. Let's say, what's the market price of electricity if demand is 16,000 megawatt hours? We can go to our system supply curve here and note that there is no point on the system supply curve that perfectly aligns with the capacity of or electricity production of 16,000. Now, what we're asking here is what's the most expensive plant that we need to use in order to meet a demand of 16,000 megawatt hours, and that is this plant that's circled here, a natural gas combustion turbine with a maximum capacity of 2,600. And even though that the cumulative capacity, if we were going to produce electricity at all of these plants, including this circled plant, and each plant was going to be used at 100% capacity, the cumulative capacity would be a lot more than we actually need. What you see is that only relying on the power plants that come before it only would give us 15,300. So you could think about this as every single power plant, the two hydropower plants, the nuclear power plants, the two coal-fired power plants, and the two gas CC plants are all online producing as much electricity as they can possibly produce, and we need 700 more megawatt hours of electricity to meet demand. And so we will have to turn on that next plant, which would be the gas combustion turbine, which has a variable cost of $60 per megawatt hour. So even though we're only using 700 megawatts of that power plant's capacity, it is setting the market clearing price. And so this would be equal to the competitive price of electricity in the wholesale market of $60 per megawatt hour. Just another simple example. What's the market price of electricity if demand is lower at 12,000 megawatt hours? So in this case, we need less capacity, but again, we don't have a level of cumulative capacity that perfectly aligns with our demand. So we're going to exhaust the first 5 power plants here, the 2 hydropower plants, the 2 nuclear power plants, and 1 coal plant. And we have 9,900, and we still need 2,100 megawatts of capacity in order to meet demand. And so we're going to tap into that next coal plant and use 2,100 of its 2,600 installed megawatts of capacity in order to meet electricity demand. And so its variable cost, shown here as $25 per megawatt hour, then becomes the market clearing price. Okay, that's it for today. Next time, we're going to do our last lecture on going inside an electric utility. We're going to talk about electric rate setting for retail customers. So please read reading number 6 for next time, and homework 4 has been assigned.